Today we're going to talk about applications of systems of equations. I'm only going to present two applications, one on curve fitting and one on electrical circuits. You can look in your textbook and other textbooks on linear algebra to see many other applications. Most of the applications require the same type, reasoning, and logic. If you understand the two applications that I present today, I think that you will be able to read the textbook and the other books and understand the other applications. First, let's look at a problem involving curve fitting. Determine the polynomial function whose graph passes through the points -1, 3, 0, 0, 1, 1, and 4, 58. Notice that we have 1, 2, 3, 4 points. So therefore it's going to take a third degree polynomial to pass through all points. Let's go back. If you know 2 points, you can determine the equation of a line. If you have 3 points, you can determine the parabola. So if you have 4 points, you can determine the cubic, or the third degree polynomial that would go through all 4 points. So since we have 4 points, we can find the polynomial function of degree 3 whose graph goes through all points. The general form of a third degree polynomial function is y is equal to ax cubed plus bx squared plus cx plus d, where a, b, c, and d are your real numbers. We can use the 4 points to create 4 equations having 4 variables. So we'll create a 4x4 system by replacing x and y by their values. So we're going to go into this general form, y is equal to ax cubed plus bx squared plus cx plus d, and we're going to create an equation for each of the points by replacing x and y by their values. So let's look at the first point. If you go back, the first point we had was x is -1, y is 3. So I replace y by 3, x by -1. The second point, we had 0, 0. So I replace y by 0 and x by 0. The third point was 1, 1. So we replace y by 1, replace x by 1. And the fourth point was 4, 58. X is 4, y is 58. So I have y is 58, x is 4. So making the substitutions, we get 4 equations having 4 unknowns. And the 4 unknowns are your coefficients a, b, c, and d. So I have for the first equation 3 is equal to a times -1 cubed plus b times -1 squared plus c times -1 plus d, because I replaced x by -1, y by 3. And you can see the other equations that were formed in a similar manner. Now we can simplify each of the equations. Negative 1 cubed is negative 1. Negative 1 times a is the opposite of a. Negative 1 squared is 1. 1 times b is b. Negative 1 times c would be the opposite of c. Plus d is equal to 3. So I just brought the 3 over this side because we're more used to seeing it this way. On the second equation, 0 cubed is 0. 0 squared is 0. 0 times c is 0. So all this is 0. So I just have d is equal to 0. When I substitute in for this, or do the math for the second one. For the third one, 1 cubed is 1. 1 squared is 1. So I have 1a plus 1b plus 1c plus 1d is equal to 1. And for the last equation, 4 cubed is 64. So I have 64a. 4 squared is 16. So I have 16b plus 4c plus d is equal to 58. Now d equals 0 will be one of my values. If I look at the other three, I'm left with a system having 3 equations with 3 unknowns. Because now we know d is 0. Since d is 0, I can simply mark it off from each of them. To get the 3 by 3 system. The opposite of a plus b minus c is equal to 3. A plus b plus c is equal to 1. 64a plus 16b plus 4c is equal to 58. So we have the 3 by 3 system. 3 equations and 3 variables, a, b, and c. And of course remember that we had d equals 0 as part of the solution. We can use derive to solve the system, so just feed into derive. I remember from tape 1, to use derive, you load derive in, you go to the author, you author the expression, and you put solve, and then you put parentheses in brackets, and you put the equation 1, comma, equation 2, comma, equation 3, comma, in brackets, comma, start brackets, and put a, b, c as a variable, in brackets, close parentheses, and then you use basic simplify, or simplify and then do it basically, and you'll get the answers that a is 0.5, b is 2, and c is a negative 1.5. Knowing the values of a, b, and c then, the polynomial function is y is equal to 0.5 x cubed plus 2x squared minus 1.5x plus, of course, the 0 because the d value is 0. So it's ax cubed plus bx squared plus cx plus d. And using these values, substituting in, I get my polynomial function. To illustrate, I went to derive, and I had derive plot the points and then plot the curve to show you that the curve actually goes through the points. So here's the graph, and this is the graph of the function y is equal to 5/10 x cubed plus 2x squared minus 1 5/10 x plus the 0. Here are your points that we had it going through. This is the point -1, 3. Here's the point 0, 0. Here's the point 1, 1. Now you're saying 1, 1. looks like it's just almost 1-0, but notice my scale here is 20, 20, 40, 60. So 1 would just barely be above the x-axis, and it is. And then we had the point 4, 58. The curve goes through all 4 of the points. Let's look at a second application. One can use Kirchhoff's laws to form equations describing electrical circuits. Now, if you've had physics, you know Kirchhoff's laws. If you haven't had physics, then you need to refer to the laws as I've written them here. Kirchhoff's first law says that all of the current flowing into a junction must flow out of it. So that means a junction cannot absorb any of the current. All the current flowing into a junction must flow out of it. And the second one is the sum of the voltage drops around the closed path is equal to the impressed voltage in the path. So you've got Kirchhoff's 2 laws. All the current flowing into a junction must flow out of it. The sum of the voltage drops around the closed path is equal to the impressed voltage in the path. I'm not trying to do a complete physics lesson, but I need to give you some physics so you can understand the application. The voltage drop across a resistor is Ri, where R is the resistance measured in ohms, and I is the current in amperes. So the voltage drop across a resistor is simply the resistance times the current. Let's look at an application. Determine the currents I1, I2, and I3. Okay, here we have an impressed voltage of 16 volts, and the current flows from the terminal around into a 4 ohm resistor. We'll call this current 1. The current comes to a junction here, and we have the current flowing this way. But out of the 8 volt battery, we have current coming this way. So we have the 2 currents coming into the junction, and we know that all the current that flows into the junction must flow out, and as it comes out of the 8 volt, it hits a resistor, a 4 ohm resistor, and the combined currents hits a 2 ohm resistor going into another junction. And as it comes to this junction, it's going to split up. Part of the current is going this way to complete the circuit. Part of the current will come this way. Well, according to Kirchhoff's first law, we know that all of the current that flows into a junction must flow out. So if I call this current I3, and this current I1, then we know that I3 plus I1, see this is coming over, so it flows in. So what flows in must come out, and it's going to come out as I2. So that gives us the first equation, which is I1 plus I3 is equal to I2. I3 goes in, I1 goes in, and it comes out as I2. All that goes in must come out, so I3 plus I1 must be I2. Now if you say, well, what about the other junction? How do I know I shouldn't consider this one? Well, what goes into this one? I2 goes in. What comes out? I3 and I1. So again, I2 equals to I1 plus I3. So either way you get the same equation. So one equation is I1 plus I3 is equal to I2. Now the second equation we can get by looking at this part of the circuit. And we know that the voltage drops across the resistors is equal to the impressed voltage, because the resistors is all we have. Well, the voltage drop is Ri. So we have 4I1, the drop here. So 4I1 plus 2I2 is equal to 16. So that's the second equation. 4 times the current 1, that's the resistor's 4, so this is Ri, voltage drop across the first resistor, plus Ri, the voltage drop across the resistor in the middle, is equal to the impressed voltage of 16 volts. So 4I1 plus 2I2 is equal to 16. Now let's trace the third circuit. 4I3 plus 2I2 is equal to 8. 4I3 plus 2I2 is equal to 8. 4I3 plus 2I2 is equal to 8. So we get three equations having three unknowns. Now we can use derive to solve this equation, or this system of three equations having three unknowns, but we do need more practice with row reduction, so I think I'll solve it that way. Now on the first equation, I can rewrite this as I1 minus I2 plus I3 is equal to 0 when I subtract I2 from both sides. So the coefficients are 1, -1, and 1. The constant is 0. The other two are already in the correct form. The coefficients are 4, 2, and 0. The constant is 16. The coefficients would be 0 because it's 0, I1, 2, and 4. And the constant is 8. So notice I put this wrong. I've got the 0 here in the wrong place. I2 is 2 and I1 is 0. So this is 0 and this is 2. I1 is 1. There's no I2. I brought it across, so I2 is negative. The coefficient of I2 is -1. Coefficient of I3 is 1. The constant is 0. The coefficient of I1 is 4. The coefficient of I2 is 2. There is no I3, so that would be 0. And the constant is 16. There is no I1, so its coefficient is 0. The coefficient of I2 is 2. The coefficient of I3 is 4. The constant is 8. So we have the matrix 1, negative 1, 1, 0, 4, 2, 0, 16, 0, 2, 4, and 8. Now we want to row reduce it. We need a 0 in this position because I worry about my first column first. The 1 is in the right place, but I need zeros under the 1s. I can get a 0 here by multiplying row 1 by negative 4 and add to row 2. So multiply row 1 by negative 4, add to row 2. Multiply row 1 by negative 4, add to row 2. One, negative 1, 1 and 0. 1 times negative 4 is negative 4, plus 4 is 0. Negative 1 times negative 4 is 4. 4 plus 2 is 6. Negative 4 times 1 is negative 4, plus 0 is negative 4. Negative 4 times 0 is 0. 0 plus 16 is 16. And then the other column is 0, 2, 4, and 8. Now one thing I can do is to reduce both of these before I continue. So I can do that by multiplying row 2 by 1/2 and row 3 by 1/2. So I could come here and multiply by 1/2, multiply by 1/2. That would give me 1, negative 1, 1, 0, 0, 3, negative 2, 8, 0, 1, 2, and 4. That just makes the numbers a little bit smaller. I could have done it earlier. I just happened to notice it then. But my first column is now okay. The second column is not. I need a 1 here. I need a 0 in this one. Well, I think what I'll do is wait and put the 1 in later. Well, I might as well. I can get the 1 there. I can go ahead and multiply by 1/3. That would be 1, negative 1, 1, 0, 0, 1, negative 2/3, 8/3, 0, 1, 2, and 4. So now I've got the 1s. But I need a 0 in this position. So what I can do is I can multiply row 2 by negative 1 and add to row 3. So we're going to multiply row 2 by negative 1, add to row 3. So 1, negative 1, 1, 0, 0, 1, negative 2/3, 8/3. We want to multiply row 2 by negative 1 and add to row 3. Negative 1 times 0 is 0. 0 plus 0 is 0. Negative 1 times 1 is negative 1 plus 1 is 0. A negative 1 times a negative 2/3 is 2/3. 2/3 plus 2 is 8/3. This would be a negative 8/3 plus 4, which would be a negative 8/3, plus 12/3, which is going to be 4/3. Now let's check that again. I multiply by negative 1. So if I multiply by a negative 1 times 1 is negative 1 plus 1. A negative times negative is positive, so that would be a positive 2/3. This is the same as 6/3. 2/3 and 6/3 is 8/3. This would be a negative 8/3 plus 12/3 is 4/3. Now I've got the ones coming. The only thing wrong here is I have 8/3 and I need 1. So what I can do now is to multiply row 3 by 3/8. So that would be 1, negative 1, 1, and 0, 0, 1, negative 2/3, 8/3, and 0 times 3/8 is 0, 0 times 3/8 is 0, 8/3 times 3/8 is 1, 4/3 times 3/8, so if I multiply 4/3 times 3/8, I get 1/2. So this is 1/2. So now we have row echelon form, ones along the main diagonal. We can easily back substitute, get the other answers. I can see that I3 is 1/2. Here I can see that I2 minus 2/3 I3 is equal to 8/3. Or I can see that I2 is equal to 8/3 plus 2/3 I3. Or I can see that I2 is equal to 8/3 plus 2/3 of 1/2, because I3 is 1/2. So that leaves me with 8/3 plus 1/3, which is 9/3, which is 3. So we get that I2 is equal to 3. I1 minus I2 plus I3 is equal to 0. So I1 is equal to I2 minus I3, which is equal to 3 minus 1/2, which is 2 1/2. So we have that I1 is 2 1/2 amps. I2 is 3 amps. And I3 was 1/2 amp. And there's the solution.